Hello. Yes. Welcome, Oscar. I hope I am audible.
Yeah. Good evening, sir.
Yes.
You are
Good evening. Good evening. Good evening. Yes. So we'll start. Yeah. So there has been a gap. We'll start after that. 2 weeks gap, I think. We are meeting at least after 2 weeks.
Yeah. Last
Yeah.
Saturday there was lecture or no lecture?
Uh, I was there. I had logged in, but uh, there was no lecture. Nobody had come.
Yes, because Saturday I was also not there. I was on vacation. But
Okay. Okay. I think you had posted also. Yeah. No issues. Even if we get around 6, 7 more sessions, we will be able to cover a lot.
okay.
So I'm starting my whiteboard.
Good evening, sir.
Good evening. Good evening. Let me see who has Shriram. Shriram. Yes. Good evening. Yes. Just yes. So we had started I think little bit about probability. So did we discuss about distributions, probability distributions? I remember we were
Yeah.
discussing.
Yeah, I think we discussed binomial. No, not
Okay.
binomial. We have discussed I think the other distribution.
Some other distribution. So it could be a binomial only. I think. Just a second. Yeah. Yes. Conditions. Yes. Yeah. Yes. So when do we say the data is binomially distributed? When the process follows certain conditions. Yeah, so for binomial distribution, the process should be following these three conditions. Process means what process? The process which is generating the data we are observing. Yeah, so the process of say tossing a coin or we observing how many cars pass through a toll booth. Yeah, so the process can be any such event which is generating some data. Yeah, if the process follows certain conditions, then the data generated will be of certain distributions. Yeah, many distributions are identified. One of them is binomial distribution. For that, these three conditions, that is, the outcome should be only two, possible outcome should be only two. There should not be any third possible outcome. Then the probability of outcome, long-term probability of what we want to observe happening once. Yeah, that is the next time we will be able to see that outcome. Say in tossing of a coin, if we are observing heads, whether the outcome is heads or not. So we are observing heads. So the probability of getting a heads, long-term probability of getting a heads is fixed. It is 0.5. Yeah. So that means if we observe a lot of past data, then we will know that the next time we toss a coin, the probability of getting a heads is 0.5, that is 50%. Yeah. In that sense, from the past data, mostly from the past data, we get a fixed probability of the outcome happening once. That is the outcome happening next time the event occurs. So in that,
Excuse me, sir. Are you sharing the screen? Because it's not appearing to me.
yes, I am sharing the screen.
Yeah,
But
I can
also,
see it. I can see.
okay,
Pastor, you can see? Okay. Maybe
Yeah, I can.
network issue at my end. Maybe I
okay.
will rejoin, sir. You can continue. I will just rejoin.
Wait. I'll also again reshare. I stopped sharing and started sharing again. Now can
Yes,
you?
sir. Yeah, I can see now. Yeah, thank you.
Yeah, I also can see. Yeah.
Okay.
Thank you.
Thank you. Yes. Yeah. And the third condition is trials are statistically independent. That is, what is happening this time is not affected by what happened previously. And what is happening this time is not affecting what will happen next time. Again, taking the example of, say, rolling of a die, if we get 5 this time, it is not affected by what we had got earlier. And this getting 5 is not affecting what we will get next time. We roll a die. That is, uh, for Ludo, we roll a die. The game of Ludo, we roll a die. So one outcome is not affecting what has happened in the past, is not getting affected by what has happened in the past, and is not affecting what will happen in the future. So that is what is meant by trials are statistically independent. Yeah. So if these three conditions are met, the data generated is binomially distributed, is said to follow binomial distribution, and it makes certain things very easy, like calculating probability in different cases when the data is binomially distributed. Statisticians have already found how to find out probability in such cases. So this is how we are able to find probabilities. Probability of X number of the outcome we are interested in, that happening X number of times out of N total number of times we have observed that event. Yeah. Or N you can also call the number of trials. That is, if we roll a, no, not rolling of a die, I hope you understood, is not a binomial uh, process, because there are 6 outcomes. Yeah, not 2 outcomes. It is 6 outcomes. It has 6 outcomes, so it is not a binomial process. But tossing of a coin, observing whether it rains or not. Yeah, that way we can define a process that it becomes binomially, the data obtained becomes binomially distributed. It rains or not. If we just observe that there are 2 outcomes. Yesterday it has rained. It is not affecting today it will rain or not. So in that sense, it is statistically independent, and we observe a lot of past data, say on that particular day, uh, or that particular month, if we observe, say, for 100 months, whether it rained or not. So in that sense, we have gathered a lot of past data. Based on that, we can calculate the probability of long-term probability of raining or not. Yeah. So in that sense, long-term probability also we can have from past data. Yeah. So it satisfies all the conditions. Now, if we want to find out in the next 5 days, what is the probability of raining on 2 days? Any 2 days out of the next 5 days, what is the probability of raining? And suppose the long-term probability of raining is 0.15. Yeah. Then what we will do? Did we discuss this much last time?
Yeah, I think we discussed that. Yeah.
Yes. So this small p is the long-term probability, that will be 0.15. Yeah. This n is number of trials, that is total number of trials. In this case, it will be 5. Yeah. And we want to observe on 2 days it rains. Yeah. We want that outcome. So the outcome of interest is x. Yeah. So x is 2 in this case. So if we substitute all this in the formula, of course, q is simply the long-term probability of failure. Yeah. So success is what we are trying to observe. Failure is when that does not happen. So if probability of success is 0.15, then the probability of failure would be, there are only two outcomes. Probability of one outcome is 0.15. The probability of the other outcome will be 1 minus 0.85. Yes, that is 0.15. That is 1 minus 0.15, 1 minus the probability of success. That will give us the probability of failure. In this case, it will be 1 minus 0.15, that is 0.85. Yeah, so Q will be 0.85. Then the rest of the things are simple. N we will substitute as 5, X we will substitute as 2, P we will substitute as 0.15, and Q we will substitute as 0.85. And this formula will give us the probability of raining on 2 days out of the next 5 days. Yeah. So in that sense, in this way, we can use the probability distribution, binomial probability distribution. Now coming to one more distribution, which is known as Poisson's distribution. After this, we will discuss normal distribution, which is the most widely used, most widely occurring distribution. Yeah. So let us have a look at Poisson's distribution. So again, what are the conditions which the process should fulfill so that the data generated is Poisson's data generated follow Poisson's distribution? Yeah. For Poisson's distribution, the average number of occurrence in 1 unit of time. Yeah. So this unit of time, we have to decide. It can be 1 hour, it can be half an hour, it can be 1 minute. So based on our observation of a lot of past data, we should be able to find out the average number of occurrence. Like a car passing through, passing in front of MIT University main gate, go through campus, MIT WPU University main gate. Yeah. So a car can of course pass in front of the main gate. Yeah. So suppose in 1 hour, and when we are observing, yeah, say we observed yesterday. So we started with 9 a.m. From 9 to 10 a.m. We saw 5 cars. 10 to 11 a.m. we observed 10 cars. So like that, for each hour, if we calculate and take the average, yeah, we do that for yesterday, we do that for day before yesterday, we do that for day before that. So say for the previous 50 days, we have that data, and on every day, the average number comes more or less same. Yeah, suppose it happens, then it satisfies this condition. If the average number is more or less constant, yeah, maybe in the second decimal place, some changes are there, some differences are there, but more or less the average from the past data, average number of occurrence from the past data is constant. Then it follows the first condition of Poisson's distribution. Then the next condition is it is possible to reduce the time interval. Yeah, that is, it is possible to have such a small time interval in which the event we are trying to observe can happen only once. Like a car passing through the main gate. Suppose now we have to make some assumptions. So suppose there is only space for one car to pass. Yeah. So that car will take, say, 3 seconds or 4 seconds to pass through the main gate, pass in front of the main gate. So that small interval of 4 seconds is such a time interval. In that 4 seconds, two cars cannot pass. Yeah. So if that is the case, if that condition is met, then we can say that the second condition of Poisson's distribution, the data being distributed according to Poisson's distribution, is met. Then the third, this explains the second condition only, the next 2 points which have popped up. Yeah. That in that small interval, the event cannot happen twice. The outcome we are trying to observe cannot happen twice. Yeah. Actually, there is some indentation error. This third point should be the third condition. Yeah. Be like this. Yes. Be like this. Yes. These 2 points explain the second condition. Then the third condition is this. Number of events occurring in one time interval, is independent of what happened in any other time interval. So the number of cars passing between 8 to 9 a.m. is not affecting how many cars pass from 9 to 10 a.m. or say any other interval, 10 to 11 a.m. Yeah. And how many cars pass between say 10 to 11 a.m. is not affected by what happened in the past. Yeah, in a way, this is same as the third condition of binomial distribution. What outcome we are observing now is not affecting the future outcome and is not getting affected by the previous outcome. So in that sense also, you can see in that uh, from that point of view also you can see. So the number of events occurring in one T is independent of what happened in any other T. So if these three conditions are met, the data follows Poisson's distribution. Yeah. Once we know that the data follows Poisson's distribution, we can find out the probabilities in different circumstances very easily. Because again, statisticians have derived a very good formula to help us in that. Yeah. So here you can look at the formula, what is lambda, what is E, what is X. Yeah. So lambda, E and X are the three variables. So lambda is that average number of occurrence. Yeah. Average number of occurrence. In a toll booth, say, if we have observed many hours for many hours and the average number is 10 cars pass through a toll booth. So lambda becomes 10. Yeah. E is the universal constant, like pi is a constant. E is the Euler's constant. Yeah. And X is the number of times we are expecting the event to occur. Yeah, number of times we are expecting success. Yeah. So, for example, suppose in this situation, the average number of cars passing through a toll naka, sorry, is 10, and we want to find out the probability of 12 cars passing in the next hour. Yeah. The average number of cars passing through the toll naga is 10. That doesn't mean that only 10 car can pass. Average means the actual number can be little more, little less also many times. Yeah. So average number of cars passing through the toll naga is 10. That is lambda equal to 10. Then what is the probability of 12 cars passing in the next 1 hour? So how will we do that? Are we connected or something else? Yes, yes, I can see everybody is there. Yes, Vishwaraj has also joined. I think, yeah, yes. So, what will be the probability of 12 cars passing in the next 1 hour, given the data? We can calculate like this. See, into lambda to the power x e to the power minus lambda by x factorial. Yeah. This is what we have. Yeah. So lambda in our case is 12, right? No, lambda is 10. The average number of cars passing through the toll naka is 10. E is the Euler's constant. This is 2.71. And this x, what is x? Is the probability we are interested in. Probability of 12 cars passing through the toll naka. Toll naka. It's a tongue twister for me. It's strange. Many people can utter that easily. Yeah. So lambda is 10 to the power 12. E is 2.71 to the power minus lambda. So minus 10 divided by x factorial, that is 12 factorial. If we solve this, yeah, we will get the value. You can solve this, you can use Excel. I hope all of you have access to Excel at this point. Okay, I think, no, it might be for some other thing. Yeah. Okay, poison, below poison only, let us try this. So the first term is 10 to the power 12. Yeah. So it is power of 10 to the power 12. So this will give us some value. is the first term. Second term is 2.71 raised to the power minus 10. So again power 2.71 raised to the power minus 10 this time. Yeah. Yeah, so it will be a very small number. You have to have more decimal places. I actually don't know how many more decimal places. So yeah, at least 15 में कुछ तो आ ही जाएगा. Yeah, okay. So it's much bigger than what I thought. Yeah. Then the third term is 12 factorial. I think the function is fact. Yeah. In Excel it is fact. So factorial of 12. Yes. So the result will be 10 to the power 12 multiplied by this part, this term, divided by 12 factorial. So the first two numbers have to be multiplied. Put bracket also. And divided by the third term. So this will give us probability of 0 point. I hope these things are visible. So this is our final probability. What is this probability about? What is this probability of? Probability of 12 cars passing in the next 1 hour. Yeah, given that the conditions, all the conditions we stated. So that is one small application of Poisson's distribution. Yeah. So Poisson's distribution is clear to,
Yeah.
to a large extent. Yes. Okay. So this was Poisson's distribution. Now coming to the most widely used distribution, normal distribution. Now normal distribution is the conditions are little different. In a way, they are easy to understand. Yeah, easier to understand. In normal distribution, all the conditions are based on the graph of frequency distribution. Yeah, frequency versus outcome. So y-axis is frequency, relative frequency, and the x-axis is outcome. Yeah. So relative frequency only becomes probability, and the outcome. So the outcome, say we are observing, say suppose weight data. So everybody in your office, we are measuring weight of everybody in your office, and we are plotting the weights in this axis. Yeah. Weight. Yeah. And then the frequency of those weights. How many people have this much weight? Say it is 40. 40 is on the lower end, 45, 50, 55, like that. Yeah. And here is the relative frequency. Say suppose there are 100 people in your office. So how many of the 100 have 40 weight? Yeah. So like that, if we plot relative frequency or probability versus outcome, the probability distribution or relative frequency distribution graph is of this shape. So yeah. Okay. So there is a very simple looking graph. Still, it follows certain conditions. So one of the conditions is this is a uni modal graph. So uni modal means what? There is only one mode. This peak, शिखर जो है एक ही शिखर है. If some data frequency, relative frequency versus outcome uh, plot of that data is like this, yeah, something like this, then it has many peaks, three peaks. So this data is not normally distributed. Yeah. Then what are the other characteristics of normal distribution? The mean of the data, will be located at the center of the graph. Yeah. So here we will get the mean corresponding to the peak. We will get the mean. Okay. Now, if we join the peak with the mean on the x-axis, this dotted line, I hope it is visible. Yeah. This dotted line divides the graph into two symmetrical parts, one left part and one right part. So for me, this is right, and this is left. So the line joining the peak of the data and the mean divides the graph into two symmetrical parts. Okay. So these are two major conditions. There is also a third condition that this graph, if we stretch it, the third condition is actually a theoretical condition. So if we stretch it, it will never touch zero, no matter how much we stretch it. Yeah, the frequency or the relative frequency or the probability will keep decreasing, but the any outcome does not have zero probability. That's what it means. Yeah, it can happen, although the probability may be very small, but still that outcome can happen. Yeah, so that's a theoretical condition. Yeah. So it will not touch the x-axis. It will keep progressing. It will keep getting extended. Even if we extend it, it will not touch the x-axis. So if these three conditions, basically two conditions, the third condition is little theoretical. So basically two conditions, that is a bell-shaped curve with only one mode, one peak, and if we join the peak with the mean will be located at the center of the graph. Mean will be located at the center, and if we join the peak and the center, this line will divide the graph into two symmetrical parts on the left and right. Yeah, let us have a look at the same conditions in printed format on PPT slides. Yeah. So these are the conditions. Mean lies at the center. Also, you can say is a condition, is a separate condition you can consider. So the curve has single peak. Mean lies at the center of the curve. A second condition. The third condition is curve is symmetrical over mean. Symmetrical over mean means what? If we join the peak and the mean, the line will divide the graph into two symmetrical graphs towards left and right. And the fourth condition, which we discussed, is a little theoretical. Two tails of the curve extend indefinitely. Yeah, it has very less practical utility. Yeah. Yeah. So this much I hope you understood the conditions for normal distribution. I hope you understood.
Yeah.
Yes. Okay. Okay. Great. Yeah. So like probability, finding probability and other distributions, we also have a formula. This formula fx equal to this whole expression. Uh, is the formula to find probability. Actually, this is the probability to find point probability. What it means is probability to find equation to find probability of just one outcome. Say one value of x. We can put x equal to that value and we will get the probability of just that uh, value. So what is the probability of having weight 48 kgs? So just 48 kgs, not below that, not above that. So we can find such probabilities with with this equation. But in probability, uh, in normal distribution, we do not use such formula. Yeah, because we are interested in finding out the probability uh, between values, not just point probability, but between values. Say what is the probability of getting weights between 42 to 50 or 43 to 50. Yeah, so we are interested in such range, and this formula becomes little complicated. Of course, we have to integrate and find that value. Yeah, put limits and find that value. So there is a easier way, widely followed easier way, which statisticians have found out. Before that, we need to understand some properties of normal distribution. Yeah. Of course, if the process generating data follows these conditions, yeah, and gives us this kind of a graph, which is symmetrical and one peak, and all these conditions are met, the data is normally distributed. In addition to that, normal distribution has some properties. So what are those properties? Those properties actually makes our task very simple. Yeah. So what are those probabilities? What are those properties of normal distribution? So say this is the normal, this is the distribution of weight, and then we draw a graph of uh, say height. Yeah, as most data is normally distributed in nature and human endeavor, so height is also normally distributed. Yeah. So the graph frequency distribution, probability distribution graph will be like this. Okay. Again, this will be height, and all the heights will be plotted here, and their frequency will be plotted here. Relative frequency or probability of each height will be plotted here, and we will get this kind of a graph. Again, as this is a normal distribution, we will have mean at the center, of the graph. And in this above case, say weight, the mean comes out to be around 55 according to what we have drawn. And as this is data, so data will have some standard deviation. Yeah. So standard deviation of weights is suppose 5 kgs. Yeah. And standard deviation of height is 0.4 feet. Say the heights are in feet, so the standard deviation of heights is 0.4 feet. Yeah. Here the standard deviation of weights is, we can write a small w here. Weights is 5 kgs, and here we can write a small h subscript. Yeah, standard deviation of heights is 0.4. Now, the property of normal distribution is the area, that is the probability. Okay, now why area is probability here? Now, yes, before that, let us clarify that part.
So,
Yeah.
the standard deviation is the how much it is deviated from the mean, right? That is the standard deviation.
Yes, on an average, in a given data set, on an average, how far are the data points from the mean?
Okay. Yeah.
In this case, mean of height, in the lower case, mean of height, and in the above case, the mean of weight. Yeah. Yeah. Now, let us try to understand this graph a little more. Yeah. So, this point, say this is 42. Its probability is something, say the probability is 0 0.01, 0 0.02, 0 0.03, 0 0.04, like that. So probability of getting 42 is 0 0.01. The next point here, probability of getting say 42.1 is this. 42.2 is this. Yeah. Okay, so we can have uh, the probability of all points between say 42 to 45. Yeah, all the probabilities. So what will be the probability of getting a value between 42 to 45? We will have to sum all the probabilities, right? We have to add
Yeah.
all the
Yeah.
probabilities.
Yeah.
Yes. That adding, yeah, that adding is basically we are adding all the lines here, all the closely situated lines. So if we add all the lines, that essentially becomes the area under the curve, this part of the curve. Yeah. So the probability of getting between 42 to 45 is the area under this curve. Yeah. So that is the understanding we need to have before we proceed. Yes. Yeah. So the probability of getting a given number of standard deviation from the mean. Now we are coming back to the property of normal distribution or normal distribution graphs. Yeah. So the area between mean, say mean in this case, which is 55, to a given number of standard deviation, say one standard deviation. So between 55 to 60, yeah, this area, which is between mean and one standard deviation, between 55 and 60. Yeah, this area, this is the area from mean to one standard deviation to the right in the above graph, and in the below graph, if we say try to plot, height is say 5 feet 8 inches. The mean height is 5 feet 8 inches. Yeah. And it is 0.4. Yeah, suppose roughly it is 4 inches. It will be little less than 4 inches. But for example, say standard deviation is 4 inches. Yeah. Or let me write only. Standard deviation is 4 inches. Yeah. So mean is 5.8 inches to 4 inches to the right. That will be 6.2. Yeah. See this point here is 6.6 feet 2 inches. 6 feet 2 inches. So the probability of getting height between 5.8 to not 6.2, 5.8 plus 4 inches will be actually 6. Yeah. So the probability of getting 5.8 to 6 feet, 5 feet 8 inches to 6 feet, this area, these two areas will be same. Okay. Have you understood this property? This is a very important property to go further. Before we go further,
So standard deviation is that symbol is called as sigma, right?
yes, standard deviation's symbol is sigma. Yes, like this.
So when we in our statistical quality control we called as a 6 sigma, that means 3 sigma and 3 sigma to both side of mean, right? So that means
Yes,
that uh,
yeah, logically yes, but in industry, when we talk about Six Sigma, it is 6 standard deviation to the right and 6 standard deviation to the left to be extra safe. Yeah.
okay.
So
Yeah.
each side 6 standard deviations, you mean, right? So,
Yes, each
oh,
side 6 standard deviation.
okay.
Our out should be our output range given by the customer should be between that. I mean, the output, the process we are following to generate any product, the output of that process should be between the range given by the customer. So if the customer wants pipes from, we are actually discussing little different things. So a customer has given, I want pipes between 2 feet to 2.2 feet half inches, 2 feet 0.5 inches. So in this range, our process should be so good that 6 standard deviation to the right and 6 standard deviation to the left should be in this range. So again, 6 standard deviation would be somewhere here, not farther. Yeah. So yeah. So this will be our target. The specification given by the customer should be within minus 6 standard deviation to plus 6 standard deviation. That is 6 standard deviation to the left to 6 standard deviation to the right. If it is not so, what do? We follow the process, something called as DMAIC. Okay. Define, measure, analyze, improve, and implement and check. I forgot what C stands for. I think it is for check. Yeah. So we keep following this process until we get this. Yeah. So that is the Six Sigma concept uh, in a very informal language, you can say.
And this one
Yeah,
sigma,
explained it.
or so what we call one
One
sigma, two sigma,
sigma,
that
uh, one sigma, actually, most of the natural processes will be one sigma. One sigma will have a lot many errors. Yeah, uh,
but how
it
we
will put.
calculate this one sigma, two sigma, for example, that by using the formulas of standard deviation.
Yes, by using the formula of standard deviation, the output specification we will measure. So the pipe example we just discussed. So we will measure the dimensions of the pipe. So one pipe's dimension we will measure, second pipe's dimensions we will measure, third pipe's dimensions we will measure. Yeah, so we will have that data and we will calculate the standard deviation of that data. Yeah, which has a very simple formula. Yeah, this xi is each value of x minus the mean of x square and sum of all those squares divided by n. This summation sign is sum of all those squares of deviations from the mean divided by n. Okay. And square root of that. I think while discussing standard deviation, uh, we have discussed this. That's what we started with. Measures of central tendency, which is mean, median, and mode. Then measures of dispersion we discussed, which is range, interquartile range also you can put, and standard deviation. Standard interquartile range maybe we have not discussed in this course, which is also simple. If we want, we can discuss. So in measures of standard deviation, we have discussed. In measures of dispersion, that is how spread out the data is, we have primarily discussed standard deviation. Yeah, which is this. Yeah. Now coming back to the property of normal distribution. So the probability of getting values from the mean to a given number of standard deviation will be same if the data is normally distributed. It could be any variable, weight, height, temperature, anything which is normally distributed. The probability of getting a value from the mean to a given number of standard deviation, say 1 standard deviation or 1.1 standard deviation or 0.8 standard deviation, yeah, that probability will be same in all the normally distributed data from the mean to a given number of standard deviation. So this is a very important property. This helps us do a lot of things. Okay. Now, when this is true, if now we can plot any normally distributed data and calculate all the areas from mean to 0.1 standard deviation, what is the area, that is what is the probability, from mean to 0.2 standard deviation, what is the probability, from mean to 0.3 standard deviation, what is the probability. We can do that and we can formulate a table, and anytime we come across a normally distributed data, which is most of the times, most of the data is normally distributed, we can use that table. So statisticians have already done that. They have prepared a table. No, not this. Yeah. This is the normal distribution table. Now they have taken a special graph, special normal distribution as the reference. What is that special graph? Yeah, that special graph we get by converting each of these values to its z value. Yeah, what is meant by z value?
That is
There are
area.
other.
Area.
No, Z value means, let me write it, then you will understand. Z value is x bar or say mu. Let me write mu divided by standard deviation. So this is the mean. This is the standard deviation. And this is the value, particular value. So in this case, in this graph, what will be the z value of 45? How will we calculate that? Z of say 45. Usually we do not write this value in brackets like this, but just for example, Z value of 45 will be the particular value, that is 45, minus the mean, which is 55 in this case, divided by standard deviation, which is 5 in this case. So the Z value of 45 will be 45 minus 55, that is minus 10 divided by 5, that is minus 2. Yeah. So when each of these values is converted into Z value, so suppose we have this data set. Yeah. Serial number 1, 2, 3, 4, yeah, say 40, 45, 50, 55, like this, and so on. So each of these values, 40 we will convert into Z value. 45 we have already converted into Z value. Yeah. Now this Z value, this all these Z values, if we plot a graph of all these Z values like this with respect to their probabilities, we will again get a normal distribution. Yeah. So that is called as standardized normal distribution. In most of the statistics part at least, the standardized means, you will come across the word standardized in statistics uh, quite a number of times. So standardized means that what we are doing now, converting each original data point into its z value like this. So here the special standard deviation, or a little bit process standard deviation we can say. So this is special in the sense it will again be normally distributed. It will have a mean. Yeah. So this mean will be what? This mean, this point will be z value of the original mean. So z value of the original mean will be what? Here in this case, z value of 55 will be what? clearing. Okay. Clearing out some area. Yeah.
So sum of all areas of the, for example, left side, sum of
So,
all the areas.
we just have to use this formula for Z. Yeah. So Z value of 55 will be 55 minus the mean, which is 55, divided by standard deviation, which is 5. So Z value of the mean will be 0. Yeah. So here we will have 0. And the standard deviation of this standardized normal distribution graph will be 1. Yeah. So based on this this standardized normal distribution, statisticians have prepared this table. Here also, from mean to a given number of standard deviation, whatever the area will be, say this is 1. So all these areas will be same because they are between mean and the same number of standard deviation. Here also one standard deviation, here also in the above graph one standard deviation, and here also this maroon color graph. So here also this area is between mean to one standard deviation. So all these areas, all these probabilities will be same, and the table is drawn based on this graph, standardized normal distribution. Yeah. So the table will be very useful. Now suppose we want to find what is the probability of weight to be between 52 to 55. Given everything, given all these discussion, probability, or at least we can write probability in short, probability of 52, weight being 52. Weight to be between 52 to 55. Given this graph, and all the discussion, what will be this probability? I'll project the table whenever you want. Yeah, okay, let me solve this one. Then the other question you can solve. Yeah. So between 52 to 55, this table is based on Z values. How to see this table? Yeah. So we convert the data into its Z value, and we see the probabilities from this body of this table. Let me show you what I mean. Yeah. So Z value of 52. Z value of 52. 52 will be somewhere here. So Z value of 52 will be 52 minus the mean 55, standard deviation of this data, weight data, which is 5 kgs. So this is minus 3 by 5. Okay. So minus 3 by 5 will be how much? 0.6. Yeah. Minus 0.6. So now look at the table. Where can we find minus 0.6? So here we can see all the z values from 0 to 3, but we cannot find negative. So what to do now? Why can't we find negative values? Any guesses? Because the graph is symmetrical. Yeah. So the area or the probability of getting value from 55 to 60, given standard deviation is 5, from 55 to 60, that is 55 to 1 standard deviation to the right, will be same as getting a value from 55 to 50, between 55 to 50 or 50 to 55, which is again 1 standard deviation away from the mean, but towards the left. Yeah. So as the graph is symmetrical, we can ignore the negative sign and find out the probability. Yeah, in this case, what we did, it is 0.6. So the probability, if we want to find out corresponding probability, we will see this 0.6 plus 0.6 here. Yeah, Z. In the Z column, we will look at 0.6, and the second decimal place is found from the body here. I think, yeah. No, there is a laser pointer somewhere. No, this is not helping. Okay, I'm not able to find the laser pointer right now. But yeah, so this area from the table we can see corresponding to Z value of 0.6 is 0.2257. Yeah. So the probability of getting a value from the mean, between mean and 0.6 standard deviations away from the mean, is 0.2257. So this probability, the answer we are looking for is 0.2257, isn't it? Yeah, 2257. So this is the probability of getting weight between 52 to 55. Is this process understood? Process of finding probabilities when the data is normally distributed. We are using something called as probability distribution table, which is this table. Is this process understood? Little bit in percentage, 80%, 70%, 50%, 10%. How much percentage is understood? Yeah. It's around 10:30. I hope you have not fallen asleep, which could be a real possibility in evenings, in late evening, late night, so to say.
Yeah.
Process understood. Okay, I think we should stop here because this requires some time to absorb. Yeah. So till this, good thing is as we are having online sessions, you will have this recording automatically through TCS Ion. Yeah, you can check out the recording once. Then in the next session, I think time is very less, and your midterm will be this weekend, 23rd. Yeah, 23rd in the usual time slot. Most probably, the timetable will be out tomorrow. Yeah, Wednesday. Yeah. So this subject's midterm will be Saturday. So before Saturday, if we can have one more session, let me know. Maybe Thursday or even Friday is fine. The same time slot 9 to 10:30 और थोड़ा इधर उधर भी चलेगा या 7 to 8 भी चलेगा ऐसा भी हो सकता है और अर्ली मॉर्निंग 7 to 8 भी चलेगा yeah so let us have more and more sessions. These are all simple things, just that after we understand something we need some time to absorb. Yeah, and maybe a couple of example problems. Yeah.
Yeah.
Yes. So let us stop here for today and let me know when you will be free uh, tomorrow or day after tomorrow or on Friday. We will have at least one hour session, short session. Yeah. Okay.
Okay.
So okay. All the
Okay then.
best. Good night.
Good night.
Yeah.
Good night.
Good night. Good night.